So this is going to be a quick recap of section 4.1, specifically how we identify extreme values. So first, I'm going to go over some definitions of local maximum, local minimum, global maximum, global minimum, and critical values. And then I'm going to go over the first derivative test, and then I'm going to go over the second derivative test. So this is a reminder of what each of those are. So definitions, first derivative test, and second derivative test. That's going to be the basis of this video. Okay, so let's get a handle on what our definitions are. So we say that we have a local minimum, a local, or sometimes we call it a relative minimum of f if f of c is less than or equal to f of x for x near c. Okay, so what does this mean? This means for all the x values around c, all the f of x values are bigger than f of c. So let's say here is f of c. All of the ones around c, all the x values around c, have a y value that is larger than the y value at c. So we say we have a local minimum, a local or relative minimum. That does not mean that farther away we don't have a y value or a function value that is less than f of c, but near c, that's the smallest thing. It's sort of like the bottom of a valley. We say we have a local or relative maximum of f if f of c is greater than or equal to f of x for x near c. Okay, so if f of c is the biggest thing around, if here's c, and here's f of c, it's the biggest thing around, so all of the function values near c are less than it. And so we have this local or relative maximum. That doesn't mean that f of c is the overall biggest possible output of f, but near c it is the biggest thing. Now, what exactly is the local relative maximum or local or relative minimum? So the actual minimum is the f of c. It is the y value. That is the thing that is the smallest. Or for the local or relative maximum, it's f of c. It's the output. That is the thing that is the maximum. So what if we take off this restriction that we're only allowed to consider x values near c? What if we cross that out and just say f of c is less than or equal to f of x for all x? Okay. Then we say that given a function f of c is the global minimum. Overall, it's the smallest thing possible if f of c is less than or equal to f of x for all x. There is no output of f that is smaller than the one at c. So it is the y value that is the global minimum. Likewise, we have a similar definition for a global maximum. Given a function f of c is called the global maximum of f if f of c is greater than or equal to f of x for all x. And again, it is the y value here that is the global maximum, or the y value that's the global minimum. The smallest output or the largest output. All right, so how do we find these local minima and maxima? Well, we start with this. Any value c such that either f prime of c equals 0 or f prime of c does not exist is called a critical value of f. So remember this. Critical value of f occurs when the derivative equals 0 or the derivative does not exist. All right, so now we're going to have two different ways that we can find our local maxima or local minima. And they're both useful. You can use one or the other. So the first one we have is called the first derivative test. In the first derivative test, and actually in both of our tests, we're going to start with a critical value of f. So let's suppose p is a critical value of f. So it's important that we find those critical values. Remember, critical values are x values where the first derivative equals 0 or the first derivative does not exist. So we're going to start with a critical value. Now the first derivative test says that if f prime changes from negative to positive at p, then f has a local minimum at p. And thinking about why that is, if the first derivative is negative, then the function is decreasing. And if the first derivative is positive, then the function is increasing. And so if it switches from negative to positive right at that value p, where either the derivative equals 0 or the derivative doesn't exist, then we have a local minimum. This should also highlight the fact that f must be a continuous function in order for this to work. Okay, so we should say p is a critical value of a continuous function. Okay. So next, what if that isn't the case? If f prime changes from positive to negative at p, then f has a local maximum at p. So if the derivative is first positive, then we have a function that's increasing, and then it's negative, it starts decreasing. That means that right where it changes, that means at p, we have a local maximum. Remember, p is the x value here. The local maximum is actually the y value. Okay, so then our other test, this is one way we can tell local minima or maxima. Now our other test is called the second derivative test, and given the situation, it might be easier to do one or the other. Okay, so let's try that one. All right, for our last reminder, this is the second derivative test. Second derivative test is also a way that we can take a critical value and test if we have a local minimum or a local maximum. So what does it say? It says if f prime of p equals 0 and f double prime of p is greater than 0, then what can we expect? Well, let's just sort of draw this situation. We have this first derivative is 0 and the second derivative is greater than 0, which means that it's concave up. So we have a concave up, and our first derivative is 0, so what do you think is going to happen? Well, we have f has a local minimum at p. Okay, so if you're ever confused about which one it is, just draw yourself a picture. It means we're concave up, so we've got a local minimum. So the next statement is that if f prime of p equals 0 and f double prime of p is less than 0, so we've got a horizontal tangent line, and we've concave down, so concave down, horizontal tangent line. So what do you think is happening at p? F has a local maximum at p. Okay. So then our last situation is that if f prime of p equals 0, so we've got a horizontal tangent line, and the second derivative is also 0, the test is inconclusive. The test tells us nothing. So the first derivative test might have been better in that case. You might have to go to other means. Okay. So our big ideas and vocabulary words are local minimum, local maximum, global minimum, global maximum, critical value, first derivative test, and second derivative test.